Hello everybody, in this video we will be discussing about stack resource policy with deadline monotonic scheduling. This topic comes under real-time operating systems. Uh, why we are merging deadline monotonic, which is a periodic scheduling algorithm, with stack resource policy, which is a resource access protocol. Because in SRP there is a step called priority assignment, which is done by deadline monotonic. So first let's discuss about deadline monotonic. What is deadline monotonic? In deadline monotonic we discuss about relative deadlines. What is the difference between relative deadline and an absolute deadline? Absolute deadline is equal to the interval of time between the time 0, absolute 0, and the actual instant at which the deadline occurs. That might be measured by some physical clock. Whereas relative deadline is the time interval. Mind it is an interval, and absolute is the actual value of time. So it is the interval between the start of the task and the instant at which deadline occurred. So in this deadline monotonic, we are concentrating on relative deadlines of every process, and the process which have lower relative deadline have the higher priority. Next, properties of DM. All tasks have deadline less than or equal to their minimum inter-arrival times, and no task voluntarily suspends itself. All tasks have zero release jitter. What is jitter? Jitter is basically the time difference between the time at which process should be started and the time it is actually starting. That time lag is known as jitter. So DM ensures zero release jitter. So the time at which task is supposed to run is run at that time only. There is no lag in that. At any instant, the task with the shortest relative deadline is executed. So if OS have multiple tasks, so it will judge on the basis of their relative deadlines. Let's understand DM with this small short example. In this example, we have 4 tasks. Task 1 have a relative deadline 3, task 2 have 5, 3, 4, task 4 10th. So we can judge on the priorities. Task 1 is assigned first priority, then task 3, then task 2nd, then task 4. But we are assuming that all tasks come at t equal to 0. At t equal to 0, task 1 will be assigned, so its priority is higher. It will execute for the 1 unit time, and it will it will release its resources, and task 3 will be executed, and then task 2 will be executed. But at t equals to 4, another instance of task 1 requests for the access of resource. So in this the priority again changes, priority again shifts to task 1. So task 2 is preempted, and in this example we can see that DM preempts the. So we can see that at t equals to 4, task 2 is completed. And task 6 has task 3 has also completed. So we have the operating system have two choices between task 4 and task 1, and then it will preempt the task 4, and task 1 is executed. Task 1 completes, then again comes task 2, and hence the cycle goes on with DM. Next we move to SRP. So that was all about the priority assigning. Now we come to the actual problem statement, which is a stack. Problem statement is that we have to allocate resources properly to the process efficiently. So in this video we are discussing a stack resource policy, which is quite efficient, and it is a better version of PCP. It works both on fixed and dynamic priority. These are few of the peculiarity about SRP protocol. It supports multi-unit resources. It limits blocking to one critical section, and it prevents deadlock, because if job is preempted, it can't resume until all the jobs that occupy stack space above it have completement. So it is basically a refinement of the priority ceiling protocol, PCP. In EDF, the preemption level will be defined as the inverse of the relative deadline of the task. So this is about EDF in SRP. SRP offers improvements over PCP, and it reduces the maximum number of context switches by a factor of 2. Let's see a few of the jargons which are related to this scheduling algorithms. First one is jobs, which is a finite sequence of instructions. Second is resources. Resources that might be of semaphore, or that might be of buses. There are several resources which are to be managed by real-time operating system. Stack space. Stack space is shared runtime stack space, which is a non-preemptible resource. Direct blocking. What is direct blocking? Job J is directly blocked if and only if there is another job holding the space immediately above the stack. So if there is a position in the stack, if process occupies a position in the stack, so it can block all the processes below that position of the stack. Priorities. Priorities is always important in RTS. Priorities. If J has higher priority than another process, we have larger values indicate greater urgency. Greater urgency means it needs to prioritize first. We need to assign CPU time first to that process which have high priority. Next important term in SRP is preemption level. This is the newest concept which makes it different from other protocols. Preemption level, the capacity of preempting a process is called preemption level. So that preemption level is decided on the basis of priorities, and priorities are decided on the basis of DM. So this is how we link DM with SRP. Two more important terms comes into the picture of SRP, which is ceiling and the system ceiling. Ceiling is basically the maximum of preemption level. The maximum process which have highest preemption level is the ceiling of that resource. Every resource have a ceiling, and system ceiling is at any instant of time the maximum ceiling among all the logged resources. So ceiling relates all the preemption level, and system ceiling relates all the resource ceilings of the process. So now we are done with all the terminologies related with SRP. Now what is the rule? On what basis this protocol works? Firstly, a task that arrives at time t can start executing only if it is the high priority task. That means it is the less relative deadline of all the tasks already present, and secondly its preemption level is greater than the current system ceiling. That means its preemption capacity is maximum than all the residing processes system or all the residing ceilings. Let's see the implementation of SRP with DM. We have taken a struct process, which is taking information about the start time, semaphores used. Our code is for two resources, that is two semaphores, which is to be shared among let's say how many process that is user dependent. We will see that within a second in an example. This is the code, and let's see the implementation part. Well, so how many processes you want to learn? Let's enter. We have 3 processes, and then enter the process of time 1 is 6. Let's enter this quickly. Let's say we have 30. Semaphore time is 0. What is the duration of semaphore? Let's say 4 units. Semaphore 1 is 1. process 3, let's say 0, enter the duration or critical section. For example, let's say for the 45, deadline of process 3 is 45, and then it's, let's say 6, 0, 1. So this is the schedule, which is firstly non-critical of 3 is assigned semaphore. Let's have a pictorial look of this thing. So basically what we have done is, at time t equal to 0, task tau 3 raises the system ceiling to priority of 1. Priority of 1, first process is highest priority since its relative deadline is less. There is a priority inversion, and tau 3 is assigned the priority of p1. Task tau 2, as it enters into the system at t equals to 3, it cannot start because priority of p2 is less than system priority, and system priority is now equal to p1, and p1 is less than p2. And then when the task t1 arrives, task t1 also cannot start because its tau 1 cannot start at t is equals to 6. Tau 1 cannot start because system ceiling is equal to its priority, and according to SRP it should be greater than. So there is no context switching, and tau 3 executes that S1 semaphore, and as it releases the semaphore at t equals to 7 seconds, and now when task tau 3 unlocks, the system ceiling goes down and all other tasks start executing. So in all other tasks we have tau 1 and tau 2, and higher priority task is assigned. Now tau 1 is executed, and then tau 2 is executed. So in this way we have shown this is the output of our code, and its graphical representation is presented here. So using these two rules, we have implemented a C code for SRP with TM. So we have seen that SRP reduces the number of preemption, and SRP is very easy to be implemented, as we don't need to do inheritance, no need to block tasks in semaphore queues. All is done using a common stack. Well, that's all for this video. Thank you for patiently listening to us.